Now, we will talk about the parametric modeling. So, for the parametric modeling, we will look at a difference equation. It is a general linear equation, shift invariant one. So, we get actually the output y n in terms of x n. So, to be more precise, few previous samples and the present sample of x n and some previous values of y n. Okay. And here we use couple of parameters, that a k's and b l's, they are deciding about the characteristics about this linear equation, and we have a gain factor, that g, that is giving that how much actually magnification would happen, and that the order of the system is given as p and q. If you look at, the p is the number of actually that the terms a k's, and that q is the number, that numbers of b l. Okay. So, that is the way it is defined, and what we get, that out of these two parts, that two summations have been given, x represents the moving average of the input x, and that the other part, the first summation, that is summation over y, that is called the autoregressive part or AR part of the system, and altogether we call this system as a autoregressive moving average system, or in short ARMA system. Here that x n in this such kind of equation, that x n could be any input, but for ARMA model, that x n is chosen as the white noise. The reason is that white noise has something commonality with the impulse, that in the previous case, in the point process, we have seen the impulse that driving that the system. In this case, the white noise is chosen in place of that impulse. That one part of it is that in the physical model, for example, for vocoder model, we have seen that different kind of input, sometimes the glottal pulse, sometimes that the turbulent air coming through from the lung. So, that turbulent air coming through the lung can be given actually modeled as this white noise. So, those are the physical, you can say, that significance, but there is a mathematical significance also, that in both the case, if we look at the autocorrelation functions, the autocorrelation function is impulse response, and that gives rise to an interesting fact, that when we look at the spectral domain, the spectrum is flat, and spectrum is flat means it has all the frequency components in equal measure. So, white noise is not lacking in terms of any frequency input. So, by now using this equation, we can choose that what part to keep and what part to eliminate. Okay. So, that is the way we can say that white noise is a rich in terms of the frequency, and it can actually help to represent any kind of output. Now, let us look more into it. Few observations first we make. The system can be viewed as a infinite impulse response filter or IIR filter, because there is some feedback loop. So, along with that, we need to think about the stability and all, but this system is an IIR system. First, we need to be aware of that. The next point is that the past input and output indicate that system has some memory. Here the output depends on present input as well as the past inputs and some past outputs also. So, that means the system has a memory. So, if there is any change in the input, that the overall output cannot change immediately because of that memory, it will require some time to get actually those memories are erased or updated by the new values, and then only we can expect that overall change in the output, or we can say that the change in output will have some inertia. Next, what we get, the model indicates that the output is a linear combination of present and the few past output. So, because it is a linear combination of the present input, past input and past outputs, we can tell this is a linear prediction model, or in short LP model. Now, if we take the Z transform, this difference equation we get in a new form, and we can derive the transfer function H z out of it, and we get two polynomials consisting of A k and B L's, that the B L part that we will get in the numerator, and the A k parts that we get that polynomial in the denominator, and we get the gain factor G. Now, here again we can make some observation. The first thing is, the system is completely determined by B L and A k's. Okay. That using these terms, that we can get that the system characteristics G is important, but not so important, because G gives a uniform scaling. It gives a uniform scaling irrespective of the frequency. So, if we are not much interested in the exact value, that means if we get a scaled version of the output, that is fine, then we may afford to forget about G. And another interesting thing, that A k's and B L's, they are equally applicable in the time domain and the frequency domain. In both the case, we see them directly, and the system can be determined or implemented if we know these values. So, that is another interesting observation. Now, we can actually represent that transfer function in different form, for example, in terms of pole 0 forms, and the same system we can actually represent with the help of the p poles and q zeros. Now, this is another representation of the same system. However, when we look at these poles and zeros, these poles and zeros have equal amount of information as the polynomial coefficients A k's and B k's, but this representation, this is more specific to the frequency domain. Actually, if we know the pole location, it could help us to know that where the PSD will have a peak, because that is determined by the location of the poles, and zeros will represent that where the PSD will take a dip. Okay. So, we can get more clear information or better indication about the frequency domain using this pole 0 model, and this thing does not have any direct counterpart in the time domain. Okay. So, now what we can do, we can look at one specific part of it. By specific part, what we mean, that we can first look at the AR part of it, or the all pole model part of it, where the output is determined by the p previous output value and the present input sample. Okay. So, that is the way we are taking only a part of it of pharma process, and we call this as AR process. So, we are concentrating on that. Now, here corresponding to that we can have the transfer function to it, as if we can go to the z domain, and the transfer function here we have represented as transfer function is represented as in this form, that we have that the poles here, or in terms of AKs here we have represented. And for the biomedical signal, this AR model actually is more common or more prevalent. The primary reason is that when we talk about the input is unknown. For the EEG, PCG, all such cases, the inputs are coming from internal body parts which are difficult to capture. So, input is unknown. In that case, what we are observing in a non-invasive way, the EEG or PCG, we only have the output. So, it is easier to model them with AR model. Okay. So, that is the way we would go ahead with the modeling, and for that AR model is the most suitable vehicle. So, when we try to predict from the past output, we get some predicted value that of y, what we have represented as y tilde. Okay. That the tilde is actually used to tell that it is different from the actual value of y, or it is an estimate of y n. And so, there would always be some amount of error in that prediction, and that prediction error is represented by that the term E n, which is nothing but the difference between the true value y n and its predicted value. So, it can be represented by this polynomial. Okay. Again, if we look at this polynomial, the coefficients are AKs. Okay. So, the polynomial is very similar to that what is the polynomial of the AR model. Now, here if we have to implement it, we should look at the signal flow diagram. We get it can be again represented as a tap delay filter, where we have some buffers or registers which would keep actually the previous values. In a more precise way, we can tell that we have a tap delay line. This is the tap delay line which is capturing the previous values of y n, and at each step we are multiplying it with some coefficients, and we are accumulating them to get the predicted value here. And if we take the difference of it with respect to y n, we get the output E n. Okay. So, that is the way we can get E n. Now, given y n, that is the signal we observe, for example, EEG or PCG, as we have mentioned in the few slides back. The parameters, if we want to calculate, that means if we want to find out the system behind it, we need to find out those parameters, and that we can do by minimizing this total squared error. Already we have defined the error term. So, if we take the total squared error, that means the overall the prediction error for this signal, by minimizing that we can actually get those parameters. In other words, we want to take the parameters in such a way that the error can be minimized or the prediction would be very near to the true signal. And if we look at that, this total square error, it is nothing but it is just a scaled version of the mean square error. In case of mean square error, we have a scaling by the term that is given by the number of samples of En, that how many predictions we have done, we should divide by that. So, by applying that condition, so we can get actually that using the minimum error condition, at that point that we take that value should be 0. Here we should just take out a just 1 minute. Here the concept is that we are going through a surface and we have some actually minima there. We are trying to find out the minimum, and when we reach that minima at this point, then if this is the direction of one say a k, for that when we reach that minima, at that point the gradient has to be 0. So, we are making use of that property, we are taking the partial derivative and we are looking for that minimum point. So, for the condition is that if we make it the value is 0, that can give us that minima. And as we have p such values of AKs or AIs, whatever the index we use depending on that, that we can get so many such equations we can get. Okay? We get p equations, and these p equations can be written in this way. In the left hand side, we are getting the terms which are having the coefficients AKs. In the right hand side, that is free from AK. So, p equations, p unknowns. So, if we know the values, that other values which are coming from the signal, now we can compute the AKs. Okay. Now, this equation, it is known as normal equation. That is another interesting point, that it is called as normal equation. The reason is, if we look at that what we are trying to do, we are trying to get actually that y tilde y n, and for that we have computed y tilde n, and y tilde n is expressed in terms of y n minus 1 to y n minus p. So, it is a linear combination of actually these past values of the output. So, now we can actually write y as a vector y n, say y n is a vector in a particular direction, and that prediction that y tilde n is another vector. Now, this one would be minimum when we have a actually we draw a perpendicular from y n to this line. Okay. So, because this is perpendicular and this value is E n, this value is E n and this value is y tilde n. So, this is perpendicular means when the error is minimum, at that time the error E n, it is perpendicular to y tilde n, means all the values of y n minus 1 to n minus p, all the past values it is perpendicular, and from there it came that to know as a normal equation. Okay. So, that is this the meaning, that why this is called a normal equation. Now, in this case, if we try to, next thing would be that what is the amount of error we have incurred. So, that also we can figure it out once we know the value of the AKs. From this equation, if we can find out the AKs, y n's are already known. So, we can compute what is the value of that minimum error, which can give us some idea that how the model has been successfully fitted with the signal. Okay. So, given this equation 1 and 2, the equation 1 is the first equation of the AR model and equation 2 is the that equation required to find out the AKs. Now, the range of minimization we can take first, that is coming from minus infinity to plus infinity, or we can say the simple intention is we want to actually minimize it over all the errors, and that can give us the form of that the summation is taken from minus infinity to plus infinity. So, when we take the summation of y n and y n minus 1, because it is a linear, it is a shift invariant process, then we can tell it is nothing but the autocorrelation of y at ith lag. Okay. Here we need to again keep in mind that we have assumed the signal is shift invariant or it is not changing with time. So, that is why we can write it in such compact form, and phi y is the ACF, and if we look at what we get in reality, in real life we can only get finite number of samples, and to be more precise, if we have n sample, we can represent it by the value of small n is starting from 0 to capital N minus 1, and in that case we have to modify the ACF estimate. ACF estimate would be limited from n equal to I to n minus 1 minus I. The reason is that outside that interval, that n equal to 0 to capital N minus 1, we do not know the value of y n. So, to keep that summation within that limit, we need to limit the interval of summation. So, that is the thing we have precisely done in this case, and we have to modify the autocorrelation function estimate what we can get in reality. Now, for that we get a little more compact form of the normal equation. We can write k equal to 1 to p, that a k is multiplied by the form that I minus k in the left hand side, and right hand side it has again autocorrelation coefficients of that phi that y. So, we have such p equations we have defined, and with the help of the p equations we can actually get the values of a k. Now, before solving that, let us look at some observation. That first thing what we note, the autocorrelation function is sufficient to calculate the AR parameters. Instead of the signals, if we had only the value of the autocorrelation function of the output signal, that is sufficient to find out the model parameters or AKs. So, that is the first thing we note, and that is a very interesting observation. Next point is the scaling of autocorrelation function does not matter, because both the sides we have the autocorrelation functions. So, if we scale, actually that scaling gets cancelled. However, the normalization of the ACF is a better way to compute those ACFs, just to avoid the overflow of the accumulators. We are accumulating the sum of product, so that does not go beyond the register. So, it is better to actually normalize them from the capacity of the machine point of view, but from the point of view of the just the equations, any scaling is fine and scaling does not matter. And in this case, we can compute the error also in terms of the autocorrelation function of the output signal and the values of AKs and the different lags of that phi y. So, what we get, that for the AR model of model order P, what all we need to know is P plus 1 lag values of the autocorrelation. That means, we need to know phi y 0 up to phi y p. We need to know that, and for a real signal we know that autocorrelation function is symmetric. So, we get the negative lags also. So, using that we can find out the values of AKs, and once we know those values, we can compute the minimum total squared error also in terms of the autocorrelation function and the AKs. So, this is the brief module on that autocorrelation function. Thank you.